Okay, so I want to now prove the quotient remainder theorem, and I've written here the salient facts. So A is an integer, B is a positive integer, and we should be able to find unique integers Q and R to have this property. A is equal to Q times B plus R, and R is in the range from 0 to B, not including B. Okay, so the entire proof, okay, is going to be based on this very specific set. Okay, so let's define S to be a set, and this is going to be a set of integers. Okay, so it's a set of integers that are actually greater than or equal to 0. Okay, so I could have just said it's a set of natural numbers, but I wanted to do it this way. Okay, the other property that it needs to have is that we can find some k such that k is an integer. Okay, and a is actually x is simply equal to a minus b times k. Okay, so this is the set that we're defining. Okay, now let's think about this for a second. Let's look at an example. Okay, and as before, let's let a is equal to 23, b is equal to 5. Okay, so the set that we're talking about is going to have a whole bunch of numbers that look like a minus something times b. Okay, so 5 times something, right? So the something has to be an integer, so let's have 0. A minus 5 times 1, a minus 5 times minus 1, a minus 5 times 2, and so on, right? Okay, and let's just put that as 23 minus 5 times 0, 23 minus 5 times 1, 23 minus 5 times minus 1, 23 minus 5 times 2, and so on. Okay, and really what I'm talking about is just 23. Okay, 23 minus 5 times 1, that's going to be 18. Okay, 23 minus 5 times minus 1, well, that's 28. Okay, 23 minus 5 times 2 is 13. Okay, and so on. The next one would be 33, and so on. Okay. Okay, so those are the numbers that are in this set. Okay, and realize that it's just simply well, it's basically the number a, and then we're subtracting for it multiples of b, but it has to be positive, right? So for example, 23 minus 50, right, is equal to minus 27, right? But that is not here. Okay, so realize that what we have here is kind of a rule, right, and a constraint, right? So the rule tells us what numbers could make it. The constraint says, oh, well, they have to be non-negative. Okay, so we're going to show that S is not the empty set, okay, because I'm going to split this into two cases. Okay, case one, let's suppose that A is a non-negative number. Okay, all right. So in that case, a minus b times 0, right, it's actually equals to a, which means that it's greater than or equal to 0. This matches the rule. Okay, it's a minus b times k, and it passes the constraint because it's greater than or equal to 0, right? So a actually belongs to the set S, right? S is not empty. That's case one. Okay, this is exactly what we did. I'll just have a running example here. Right, when a is 23 and b is 5, right, then case 1, right, that's where we're at. Okay, and what we say is that 23 belongs to the set S. Okay, so now let's try case 2. A is less than 0. Okay, well, I can't just, I can't just choose a. A won't be there because a is a negative number, so it actually doesn't belong to S. Okay, but this is what I can do. Okay, a is less than 0, so minus a is greater than 0. Okay, that's just a simple thing, right? B is also greater than 0. Okay, so b minus 1 is greater than or equal to 0. Okay, so what I found is a positive number and a non-negative number. Okay, so I can conclude, okay, that minus a times b minus 1 must be greater than or equal to 0, right? I mean, I have a positive number by a non-negative number. That has to be non-negative, okay? But actually, one of the things this means is that a times 1 minus b must be greater than or equal to 0, right? And that's clear because all I've done is I've taken the negative numbers, negative 1, and multiplied both of those factors by minus 1. All right, so now let k equal to a, okay? And what I have is that a minus bk, right, is actually the same as a times 1 minus b, right? You know, just factor in the a. And I already showed that that's greater than or equal to 0. So here is my rule, right? This number, whatever it is, satisfies the rule, okay? And it passes the constraint, right? So what I can conclude is that a minus bk, which is actually equal to a minus ab, right? Okay? Or I guess I can also write it as a times 1 minus b. I mean, these are all the same number. They all belong to the set S. Right? So a is equal to 23. Actually, let's make that minus 23. What am I saying? And b is equal to 5. Okay, so we're clearly in case 2, right? And the number that is guaranteed to be here is minus 23, which is a, times 1 minus b, 1 minus 5. Okay, so what we have is 23, right, times 4. Okay, and what is that, 92? Okay, so 92 must belong to S, right? It belongs to that set that we're talking about. So that's what this part of the proof does. We now have this set S, and we now know that it is not empty. Okay, so we know that S is not empty, right? We just proved that. Now S is a set of natural numbers, okay? So S is a subset of the natural numbers, okay? Now, you remember when we talked about well-orderings, right? And one of the things we said was that, well, the natural numbers are well-ordered. That's kind of our canonical well-ordered set. And we said that there were two ways to define well-ordering. One of those was about having no infinite descending chains, right? And the other one said that if you have any non-empty set, then it actually contains a least element, okay? Well, here it is, right? So S has a least element. And let's give it a name, right? Say M. M is just a number, okay? So what do I know about M? I know that M is equal to a minus bk for some k. Okay? I also know that M is the smallest. Number in S, right? So it means it's the smallest number such that the number is non-negative and can be written as a minus bk. Okay, and that just follows because it's the smallest element of this set, and this just describes all of the elements of that set, and it has to be, you know, less than or equal to all of them. All right. So what I now want to do is kind of to make an argument about M. Okay, so I want to claim that M has this property: it's less than or equal to, I mean, it's greater than or equal to 0, and it is less than B. Okay, now this part I get for free, right? Because M belongs to the set S, so most definitely it has to be greater than or equal to 0, right? That's the constraint. Okay, so how about M being less than B? Okay, well, the proof of that is this. Let's take a look at M minus B. Okay, and let's call that M prime, just so I don't have to keep writing that. Okay. Okay, so what exactly is this equal to, right? Well, that's going to be equal to a minus bk, right? For some k, because that's what M is, right? Minus b. So that's a minus b plus 1 times k. Okay? Right? That's what that number is. All right. M prime, right, is obviously less than M, right? I mean, that's just by definition, because it's M minus B, where B is some positive integer, okay? So M prime is not in S. It's very clear, right? Because S is always a set of non-negative numbers. So m prime can actually be written as this form, right? So m prime passes the rule. That's what that tells us, okay? What that means is that m prime must be less than 0, right? Because if it wasn't less than 0, then it would actually be in that set S. Okay? So what do I know? M minus b, that's what m prime is, right? Okay? Is less than 0, and that just implies that m is less than b. Okay? So here's what we discovered. We've discovered using this this funnily defined set that in fact A, or rather that in fact well, A can actually be written as x plus bk, right? And in particular it can be written as m plus bk, and m is a number between 0 and b. Okay, so here's what we can now say, right? A can be written as bk plus m, okay? This should be okay. Okay, bk plus m for some k, right? And 0 is less than or equal to m and is less than b. Okay, that's what we just learned. So now we're going to use that, okay? Because I'll just say let q equal to k, whatever k that was, and r is equal to m. Okay, and so now what we have is that A is equal to q times b plus r, and 0 is less than or equal to r is less than b, and this is the existence part of the theorem. Okay, so we've actually proved that there are integers q and r such that a is equal to qb plus r, and r is in the range between 0 and b, not including b. Okay, so that's great. We've done half the proof. Okay, so what's left is the uniqueness. Okay, and let's do that now. Okay, so we took care of existence. Okay, so now we want uniqueness. Okay, so how do we do that something is unique? Well, remember the way that we always formalize unique. What we say is, suppose there's 2 of them, I'm going to show you that they're equal. Okay, so suppose that there's 2 of them, right? And so that would mean that A is equal to Q1 times B plus R1, and A is also equal to Q2 times B plus R2. Okay, so I got 2 Q and R's that work. Okay, well, in that case, here's what I'm going to do. I'm just going to subtract them, right? And I will end up with Q2 minus Q1 times B is actually equal to R1 minus R2, right? You know, just rearranging terms. Okay, now let's assume, and the phrase that mathematicians like to use is assume without loss of generality, meaning that this assumption is harmless. They usually write that as WLOG, without loss of generality. Okay, and we'll assume that R1 is the larger of the remainders. Okay, R1 is greater than or equal to R2. If the assumption were false, then I just swap Q1, Q2, R1, R2, right? So that's why it's without loss of generality. Okay, so that means, okay, that R1 minus R2, right? Well, let's see, how small can it get, right? R1 is greater than or equal to R2, so this has to be greater than or equal to 0, right? Okay, now how big can it be? Well, R1 is a number that is smaller than B, right? Because you know, that's what we showed. And R2 is also smaller than B. So R1 minus R2, the biggest that I can make it is if I choose R1 to be B and R2 to be 0. So that actually has to be less than B. I said R1 to be B. I can't quite do that, right? I can't go that large, B minus 1. That's why it's a less than as opposed to a less than or equal to. All right. Now, R1 minus R2, right? What do we know about that? Well, R1 minus R2 is just Q2 minus Q1, okay, times, so this has to be, Q2 minus Q1 times B, okay, right? That's from here. That is less than B. All right. Okay, this is a big moment. Q2 minus Q1 times B is less than B. Okay, everything that you're seeing in front of you is an integer. In fact, the B is even greater than 0, right? So how can this possibly happen? Okay, well, since this is an integer, right, it can't be any smaller than 0, right? Because remember, B is actually positive, right? So if nothing else, I can just divide everything by B, and I end up with 0 is less than or equal to Q2 minus Q1 is less than 1. Okay, remember, B is positive. Okay, so for that to be true, since Q2 is an integer, Q1 is an integer, I'm subtracting integers, I have an integer. There's only one integer that is greater than or equal to 0 but less than 1. Okay, so this means that Q2 minus Q1 must be equal to 0, right? Or Q1 is equal to Q2. Okay, awesome. So we've learned something. We've learned that at least the quotients have to be the same. Okay, so we know from our little argument here that Q1 is actually equal to Q2. So A is equal to Q1 times B plus R1 is actually equal to Q1 times B plus R2. I'll just substitute it Q1 for Q2, right? Well, let's just subtract Q1B from both sides, and we end up with R1 is equal to R2, right? And there's the uniqueness, right? So we're done. Uniqueness is finished, and we've completed the entire proof of the quotient remainder theorem.